Okay, let's have a class, and we will do a review this time, and also we'll finish this lecture 5 slides. Then, as scheduled, we postpone 1 day, so next week, Tuesday, we'll have open book exam 1 as a schedule. When we finish here, we're going to do a little bit of review. Like I said, the open book will be, you can open any of the textbook, your notes, your computer, as long as it's not internet. Okay, eCampus is fine, but not the Google, and not talk to each other, sit a little bit separately, not send a short message. As long as we finished about 1 hour 50 minutes individually for exam paper, then that should be fine. And the exam question will be routine, multiple choice, true or false, short answer, all those things. Okay, I'll have a couple of examples I will mention. So let's just finish this section, but I want to do a review first, what we talked about. So I have several media here. We want to do a very brief review, but something we're going to talk. Okay, I have a TSA agar. This is obviously is most of the bacteria can grow, so it's a support media. This is based on the function, and of course, this is a solid media. And this is a complex media. I want to say most of the bacterial media is complex media, and barely we use in the food microbiology lab, unless you realize the chemicals, and you wanted to cultivation biofilm. Otherwise, vegetables themselves, it's all complex media. And we mentioned this guy is a neutroblast. It's a blood agar. And we talked about the blood agar, and we said this is using 70% sheep blood. Because of the hemoglobin, so it's a lot of nutrients there. So this is an enriched medium. So bacteria can grow dramatically. Now, of course, this is a complex media, but more important, this is a differentiated media. Okay, why we say it's a differential media? Because it could be categorized as alpha hemolytic, beta hemolytic, and gamma hemolytic. And the alpha hemolytic, we say it is a little bit of green color. It is incomplete hemolysis. Good example, Streptococcus ammoniae. And the beta hemolytic, it is transparent zone. And a good example will be Streptococcus pyogenes. And the gamma hemolytic, it is nothing happens. Okay, that's very important for the blood agar. We're going to mention what kind. Then we talk about the chocolate agar. Looks like that. So chocolate agar. Chocolate agar, this is a blood agar heated at 70 degrees Celsius. And this is used to cultivation of fastidious bacteria. Which means the bacteria are very picky for the environment to grow, let's say Campylobacter. And we also mentioned a couple of things like a Haemophilus influenza, like a Neisseria gonorrhea, all those type of the human disease pathogen. Looks like that. Turns brownish color, so it looks like chocolate, so we say it's a chocolate agar. And then we mentioned a very important Mercanti agar. And the Mercanti agar, there is two major ingredients there. Number one is crystal violet. That's why it looks like it's a purple color, because crystal violet will kill all gram-positive bacteria. So only gram-negative bacteria can grow. And you know the reason, because crystal violet will contact and destroys the gram-positive bacteria, the heavy peptidoglycan. And the gram-negative bacteria is just very sick, so it's not affect too much. Second, they have a lactose. Therefore, this is a selective medium. No question about it. It is also a differentiated media. Differentiated media based on the lactose fermentation difference. If the lactose fermentation positive, it is pink colony. The reason, because we have an ingredient called neutral red there. Okay? And if it's lactose fermentation negative, it is colorless. And we also mentioned about that McConkey agar, most of the time we should say McConkey lactose agar or lactose McConkey agar, because we have a sorbitol McConkey. Sorbitol McConkey, which means instead of you have lactose, you have a sorbitol. So this is also have a sorbitol positive and sorbitol negative. And we mentioned that this is we could do is a Shigei toxin generated E. coli, STEC coli. On the sorbitol agar, it is sorbitol fermentation positive, so it is a little bit pink. And the traditional E. coli, let's say 0157H7, that is negative, so it is colorless. So if I want to draw a picture here, I have E. coli, 0157H7, I have STEC, Shigei toxin E. coli, and I have a traditional McConkey agar, and I have a sorbitol McConkey. So what's going to be the table looks like? It should be positive, negative, negative, positive, and this is pink, and this is pink, and this is colorless, and this is colorless. So that's very important. Exam, I could have a question for you. I could say, assuming you're working in a meat plants, and there is outbreaks recently happened, and you are a microbiologist. After doing the molecular stuff, you know it is Shigei toxin E. coli, STEC, or it's E. coli 157H7, which media you should use, what the result looks like, then there will be a very good answer there. Okay, so you just draw the table. I mean, it's a very good question. It's an applied question. And we left one agar we haven't mentioned. One important agar we haven't mentioned is this guy, is mannitol salt agar. So we want to talk about this mannitol salt agar. I'll just write here. Okay, mannitol salt agar. Mannitol salt agar, it is very similar to McConkey agar. First of all, this is a selective medium. Why it is a selective medium? Because we have a salt there. Okay, salt. This is usually about like 3% salt. Salt will cause osmotic imbalance of bacteria, cell wall, cell membrane system. So lots of the bacteria will be died. Only which group of bacteria will survive is called halophile. Now, which bacteria is halophile? Staphylococcus, aureus, or other staphylococcus. By the way, you don't have to worry about the bacteria name, and I will put there. I will add there at the top if you need it. Okay, you don't require to remember, because this is a general education class, not a major. If microbiology major, then you need to know the spelling, all those things. Staphylococcus is the halophile, which means they like salt. And I said it's on the skin surface, It is widely existing, okay, Staphylococcus aureus. So it's a selective media. For example, E. coli doesn't grow. E. coli will not grow because they cannot survive with salt. Second, this is a, we call this is a differentiated media. Why we call it a differentiated media? Because they have a mannitol. Same as the lactose, mannitol is a sugar, so there could be mannitol fermentation positive and mannitol fermentation negative. Now, what it's going to be looks like if it's mannitol fermentation positive? If it's mannitol fermentation positive, the colony is yellow colony. If it's mannitol fermentation negative, the colony, it is colorless. Now why? Because once it's fermented, it will generate acid, which means the pH will be go down. And in this medium, we add a pH indicator. It is called phenol red. What means phenol? Is this guy means phenol? Is that right? So let's say this guy here, phenylalanine. If it's amino acids, that's phenol. Phenol indicator, it's a phenol red. The phenol red, what happened is very interesting. We mentioned about at the pH 7, this is pH 1, this is pH 14. At pH 7, it's colorless. I will just say original color. At pH 1 or pH 3, 4, this is going to be yellow. And at alkaline environments, pH 14 or 13, 12, this will be cherry red. So that's why this is a pH indicator based on the color. And here, the mannitol fermentation, you add a phenol red there. If it's mannitol fermentation positive, it's yellow colony, otherwise it is colorless. Now why this is important? Because this is can differentiate Staphylococcus aureus and Staphylococcus epidermis. This is a pathogen, this is a non-pathogen. This is a pathogen cause food intoxication, and the Staphylococcus epidermis is a normal bacteria on the skin surface. And on the mannitol salt fermentation, what it looks like, this is positive and this is negative. And this is positive and yellow colony. Okay, that's why it's basically it's colorless. So that's a mannitol fermentation argument, mannitol salt argument. Then there is a question. I want to just jump to here to let you guys do the question. Let's just example. This are exam questions. So we just mentioned mannitol salt agar. Okay, mannitol salt agar only allows the growth of halophile. Now I already make your life easier. I said salt-loving microbes like salt. Non-halophiles will not grow. That means it's a selective medium. Among the halophiles, mannitol fermenters will produce acid that turns the pH indicator yellow, and the mannitol non-fermenters leave the medium red, which means it's colorless, original color. Onto MSA, you inoculate a halophilic mannitol fermenter and a halophilic mannitol non-fermenter. In this case, this media is acting as what type of the medium? Can you tell me the answer? Give you 30 seconds. What is the answer? This is the MSA agar? Yeah, you can just tell. It's a selective media? A? C. Yeah, C. That's lots of people will choose C. Then do you think it's correct or not? What is the mistake you have? No, I appreciate you answer the question. That's good. But this is a common mistake lots of you will have. We just mentioned the magneto sort arc is a selective media and differentiated media, so you just pick C. But you have to read the story. What the story tells us. So the first section right there, Q here, you are talking about is the introduce of magneto sort arc. Is that right? The sentence until here. Until here, you actually introduce what is magneto sort arc. Okay, read the last sentence. Onto magneto sort arc, you inoculate a halophilic magnetofermenter and a halophilic magneto non-fermenter. In this case, this media acting as what? Okay, the first question, you inoculate a halophilic magnetofermenter and a halophilic magneto non-fermenter. Does the bacteria gonna grow? That's the first question. You tell me it is a selective media and a differentiated media, then I'm adding two bacteria there. If it's selective, one will grow, another one will not grow. So my question, if I'm inoculating a halophilic magnetofermenter and a halophilic non-fermenter, is that going to grow? Is that grow or not? How many of you think it will grow? It will grow. Of course, yes. Did that grow? Yeah. Why?
Because they're both.
Yeah, because they are both hemophilic. They're both halophilic. They like salt. So they both grow there. What's the difference? One is a fermenter, another one is non-fermenter. So what's the difference? The color of the colony will be different. Is that right? One of them will be yellow, another one will be colorless. So at this moment, this media is acting as a differentiated media. Is that right? Yes, that's the answer. Okay. Let's do a change of the question. Okay. The top of the same. It's magneto sort arc. I'm going to add is a halophilic fermenter. Fermenter of magneto. And then I'm going to add a non-halophilic fermenter of magneto. Then what's the function of this media?
It's selective.
Yes, it's a selective media. Because regardless of magneto or non-fermenter, this will not grow. It cannot survive the salt. The salt already killed it. So you don't talk about, which means it's not existing, so we don't talk about anything further than that. It's yes or no, it's already no, we don't talk about morphology or color. Okay? So that's a very good practice question for you to think about. And I will say these type of things are difficult, but the tricky thing is here. Do not take it for granted, because in the class we talk about the MSA, arc is a different sheet, and the selective media, so you don't even read it. Then you pick C. Then you lose the point. So it doesn't matter it's open or closed book. Is that right? So what the key thing is that read the story. That is very important. Okay? Don't take it for granted. Okay, so that's something we want to mention first. Okay, next just couple of things I want to go over a little bit easy, because the reason is we don't have a lab, and the lab will be very late, so it's going to be very abstracted if we spend lots of time. This is called the isolation of the pure culture. And I will say the isolation of the pure culture, what we do is the one we mentioned earlier, is using streak plating. So very intensive at the beginning. And then you flame the loop, less intensive here, and more less intensive at the final. And you see the colony there. This colony is the isolation of pure culture. Okay, that's colony. So this is called streak plating. Now, what is spread plating? Streak plating we talk about here. You're not gonna know the number. It is yes or no. So I have a solution. I took it out. I spread it. If it's grow, it have a single colony. We know there is bacteria there. If it didn't grow, we know there's no bacteria. But we don't know the number. So what we're going to have to do the number, we have to do spread plating. So that's a spread plating. Spread plating, you're using an agar. The agar is already there. And I'm going to add the liquid. Then I'm using spreader to spread. So, give you an example. From the neutral agar, of course this has to be underneath the hood. I have a liquid pipette, I'm pipetting it, is 0.1 ml. Then you use a spreader to spread it. Very well. It will be covered on the surface. And then I put this into the incubator at 35 degrees Celsius 24 hours. You'll see the colony. And what the colony looks like? It's like that. Okay? The colonies looks like that. Now, so you have a question for me. How do we know how many it is? Then you're going to have to count. It's like you count an apple. Okay? So, you have to have these colonies, then you're going to count these. You have to manually count. Then you're going to say, okay, it's too many. Therefore, in the microbiology area, we have acceptable zone, which is 30 to 300 CFU, colony forming unit. That is acceptable zone. More than that, we think it's too many. Less than that, we think it might be cause cross-contamination. So 30 to 300 is acceptable zone, usually. Okay? So that's bacterial. Now, we have another one. It's called pore plating. Spread plating is this agar already made and add the liquid. What is pore plating? Pore plating is using melted agar. So if we do pore plating, you're pouring the bacteria mediums in. So we use melted agar. How we do? You need a flask. You need a jar. You know agar could melt it, like the French pudding. And then you dump it here. Or you use a pipette to pipetting about like 25 ml there, and then put it at room temperature. But at the same time, what you're going to do? You're going to, when you pour, or before you pour it, you're going to add the bacterial liquids first. And then you pour it. And then you mix it. The bacteria and the agar media will be solidified at the same time. That's what's a pore plating. Now, what's the advantage for pore plating?
Would it be the temperature?
Yes, that's a good thing. We'll get to that. What's the advantage of this? This saves you time. Because if you do spread plating, the agar has to make it first. Then I'm cultivation bacteria. Now the pore plating, the medium and the bacteria I could add at the same time. So this saves you time. Second thing is you have a good point there for the temperature. Pore plating, because it's a melted agar, so the temperature a little bit higher. Usually how high it is? Could be 50 degrees Celsius. So which means the number after pore plating is a slightly lower because the mild heat will kill bacteria. So compared to the spread plating, pore plating, basically you get a little bit lower number. Okay? So that's a pore plating. Now there is something I want to say. Spread plating and the pore plating, we want to know the quantify of the bacterial colony. Strict plating, we only need to know yes or no, the presence and absence. But are they all going to have isolation of the pure culture? Yes, they all will have isolation of the pure culture. But the purpose for pore plating and spread plating is to get the exact number. Okay, so that's something I want to emphasize. This one I'm not going to talk too much. In my another class, or major students are required to do the calculation, but some of you are not even major, so we don't require to do, we just let you know. If I have, let's borrow the bottle, okay? If I have a bottle, I want to test how many bacteria there. Let's say this is the bottle is contaminated with E. coli. Can we just add liquid onto the agar and then spread it? Yes, we can. But we have a limitation. It's 30 to 300 CFU on the agar plates. So you cannot put a high density, high concentrated bacterial solution onto the agar. How about if this is not a water, this is like an apple juice, let's say, contaminated with E. coli. It grows fast, the bacteria is filled up the water. What we have to do? We need to do a dilution. Okay? So before we testing the bacteria in the apple juice, we need to do a C-area dilution. The C-area dilution is either 10-fold or either 100-fold. I just want to let you know, I will not give you a mass to do it because it's completely mass. If you already taken chemistry class, it's easy. If you never took, it's very difficult. So what we do, we usually add 1 ml, go 9 ml, or 0.1, go 9.9. It's a 10-fold or 100-fold C-area dilution. That's what we call it. Okay. So we prepare multiple tubes, and this is tubes. We have 9.9 ml. Then the original tube, we're going to add 0.1 ml, mix very well, 0.1 ml, go to the second one, go to the third one. This is called 100-fold C-area dilution. And we also could do is, instead of using 9.9, we are adding 9.0 ml. And the original right here, we added 1.0 ml, they mix very well, then 1.0 go to the second one. That's called 10-fold C-area dilution. In my major class, we had a calculation about that. It's basically you test your mass. But I just want to tell you, you have to do is a dilution to get that point. Otherwise, the number, the colony on the plates will look like awkward. Okay, you're not going to see the very clear colony there. So this is what we call it a spread plating, pore plating. The technology we call it C-area dilution. Okay, this is called spiral plating. This equipment is expensive. It is about $20,000. What's a good thing for that? Sometimes we want to test the bacteria in the liquid. Let's say I want to test the bacteria in the Coca-Cola, how many it is. I'm not going to do spread plating because it's too much dilution, too many dilution tubes. So I use this spiral plating. This spiral plating, the good thing, it will cover multiple dilution factors. So you have like a pump here, negative pump. You have, this is the liquid water, and this is the alcohol. The pipes, you can clean it, sanitize. And then when you press the button, it will do the stir. And you can see the colony looks like that, and this is the automatic reading machine. You put in the machine, they will read it. And this is used crystal violet to show the demo. And in the older time, if we do not have an automatic reading machine, we use this kind of card and this kind of ruler to measure, then we get the number. Okay, so that's a spiral plating, just want to let you know. It's some kind of machinery stuff to calculate counting bacteria. This is something else I want to mention. Bacteria on the agar will have a different morphology. So let's do an example. I could do an example. I will show you next week. I have a bacteria here. Okay, I'll use my hands to touch it. We'll see what it looks like. I have another agar, which is a mannitol salt agar. Let's see whether we have Staphylococcus aureus. I touch it. I have a Macanthi agar. I also touch it. Okay, we'll see what it looks like. I'll put it in my office next Thursday after exam. Blood agar. Hope they're the better hemolytic. I don't want to touch that. It's the same thing. So I use my hands to touch it. We'll see the colony, what it looks like. So different bacteria on these agar plates, they have a colony. And these colony also have a morphology. So you see that could be single, could be circular, could be punctiform, and the elevation could be flat, raised, convex, and the margin could be entire, lobate, erodes, filaments. So this is called colony morphology. Now why it is important? Some of the bacteria, especially the pathogen, the morphology on the agar plates is important. For example, Neisseria gonorrhea grow on the chocolate agar, it's the pushable colony. So once people have a Neisseria and who is difficult to pee, have an abdomen pain, abnormal discharge in the vaginal tract, let's say, they go to see a doctor. When you have the plates, have a chocolate agar to want to test Neisseria gonorrhea, you can see those pushable colony. So colony morphology is important to diagnose some of the bacteria. Okay, next one I want to mention is some other methods called testing the number of the microorganisms. The first one we know is on the agar plates. It's a colony we call counting. We also have other methods. This is what we have to do is a chamber. This chamber will put on a bacterial liquid, we put a cover slip, and you will see those tiny dots there. And underneath the microscope, you can count them. However, there's a disadvantage for counting the chamber. What's that? You cannot differentiate a live and dead cell because everything is there. But on the colony, on the plates, it is a live cell. So always remember the colony on the plates is a live cell, and the colony, you see those cells in the chamber, in the liquid, we don't know whether it's alive or dead. Because even you heat it, even you do the autoclave, the colony, the cell still there in the liquid. And on the agar plates, it will not. Okay? Another thing, this is you learned in your chemistry class. We could test the turbidity of the bacteria. Some of them, we think the turbidity is really, really huge. That means bacteria grow dramatically. Sometimes we didn't see any cloudy or turbidity. So we're using a color spectrometer, and we can test the absorbance at a certain wavelength. So let's say you have a 0.21 and 0.04. We know the cell density of 0.21 is larger than 0.04. However, again, we cannot differentiate whether a bacteria is live or dead because it's all in the cell tubes. We only know the original density. We don't know they're live or dead. Another thing what we can do, we can use a funnel to do it. Negative pressure the funnel, and we can put a membrane filter paper. We will know the pathogen. The membrane filter paper, this one is using 0.45 micrometer. This is most of the time the bacteria will not passing through because that size will be prevent the bacteria going through, and yeast and the molds will stay there. Now, what is this one used for? This is used for testing our municipal drinking water. In the United States, the tap water, you turn it on, ideally you can drink. Because we did the colonization, we did some of the treatments. And of course, there's the hard water, soft water, all those things. We should talk about the magnesium and calcium, that's a different story. From a microbiology standpoint, our municipal water is drinkable. Because the drinking water, they use these type of testing to see the viable counts. They require zero tolerance for coliform and the fecal coliform. The difference between coliform and the fecal coliform is the incubator temperature. Coliform 35 degrees Celsius, fecal coliform 44.5 degrees Celsius. It should be zero tolerance, which means your drinking water cannot find one colony, even one cell of coliform and the fecal coliform. Because otherwise, which means the drinking water is contaminated with human or animal poop, which is a fecal sample. That will be very dangerous. Okay? So that's using the funnel to do the test. Another one is a long time ago. I did when I was the first job working in the company in Seattle. This is the ISO grade. Very similar to the funnel. However, what's the difference? They are using it for test of fungi. This is for yeast and molds. They are not for bacteria. The film you put it there, the negative system, and the pump is there, generate a negative pressure, and the liquid will down, and the bacteria will stay on the film. And this will be showing you there's lots of the black colony there, which indicate the yeast and the molds, the fungi, how many it is. Okay? So that's a membrane filtration system called an isograde. So we finished talking about here. We will be doing some of the review for the exam. Let's go back to see all these slides. Very important, since it's an open book, so you don't have to remember, but you need to know what we talk about. So what's the first lecture we talk about? Little bit introduction, little bit of history. Okay? So we talk about what is microorganism, too small to see your naked eye, and there is a different category. And when we talk about the bacteria, it is cellular. And a good example is E. coli. That's we mentioned all the time. And then we say it's always bad, but sometimes it's going to be good. Now, then we move on to the history. So you need to know the person's name. Who is the person the first time find the vaccination? To conduct a vaccination is Edward Jenner. That's a name you should know. Okay, then I have a question for you. Talk about vaccination. MMR, mumps, measles, and the rubella, using what type of the vaccine? It is attenuated vaccine, is that right? And the whooping cough, meningitis, using what type of the vaccine? Is purified antigens used. And these things you should know a little bit. Who is the person discovered the microorganism? Anthony van Leeuwenhoek. You know, it's simple. Who is the person from microbiology level to stop the theory of spontaneous generation? Is Louis Pasteur and the very famous swan neck flask. And the final below to the theory of spontaneous generation is John Tidal and Ferdinand Kohn. They find the heat-resistant bacteria, and Ferdinand Kohn find a single spore. Okay, Bob Koch. Very simple, short answer question. What is Koch postulate? Can you do that? 1, 2, 3, 4. Is that right? You can copy the sentence or you can write your own. As long as you touch the points, it's fine. Okay? This will explain the relationship between microorganism and the disease. Now we talk about the agar. Who is the person behind the agar? Well, Fanny has he find the agar. What's the components of the agar? Polysaccharides of seaweed. It's a pure culture. So what we do? Strict breaking. Naming, classifying microbes, genus name, species name, binomial nomenclature. Which one is the exception? Salmonella, is it right? We mentioned Salmonella is the exception. Salmonella typhimurian, the typhimurian is not italic because it's a subspecies name. That could be a very good question for you. Why Salmonella typhimurian is a little bit different from the E. coli? Because that's a subspecies name. The full answer, you could say there's a Salmonella enterica, subspecies enterica. Is that right? So that's a very good question. That's what we finished the first one. Slide number 2. This is the one we talk about these basic microscopy. And we spend a lot of time talk about bright field microscope. Okay, very simple. What is the total magnification? Do you remember the resolution power, the formula? If you remember the P equals lambda divided by 2 and NA, so which means the shorter wavelengths, the resolution power is going to be decreased, but the resolution capability is increased. Shorter wavelengths indication greater resolution. So we want to control that the wavelength has to be short. This tells you total magnification. Can you do the calculation? Yes, it's easy. Ocular lens multiplied by objective lens. Why we need oil immersion? To remove the air gap. Is that right? The reason is to remove the air gap. Dark field microscope. What is a dark field microscope? We put a block underneath it, so the light going through the specimen is perpendicular. And this used to identify a very special bacteria called spiral sheets. And a good example is Treponema pallidum called syphilis. And there are some others. Borrelia burgdorferi causes Lyme disease. Leptospira interrogans causes jaundice, is a liver disease. Phase contrast microscope. What is the big advantage of this one? There is a phase ring there, so can change the wavelengths. The wavelength phase changed, so it's going to be shown up because finally it's going to be overlap at the end. What's a good thing? It can go in to see the internal structure of some of the eukaryotes. And this is a very good picture, show you the difference between the bright field microscope, phase contrast microscope, and also the dark field microscope. Fluorescence microscope, using the Davy stain, fluorescence dye. What's a good thing for this? It could differentiate the live and dead cell. Is that right? Live cell is red, dead cell, live cell is green, dead cell is red. A laser confocal microscope, when we use it, it will generate 3D images because this used to testing a special bacteria is called biofilm. So I could ask you, what is biofilm? We have a definition for that. A matrix of bacteria on the surface. Which tool we should use? Well, laser confocal microscope. But sometimes you say it is a scanning electron microscope. That's okay. It's both we could get to know the 3D images. And then we talk about the electron microscope. This is scanning electron microscope, transmission electron microscope. Which one could see the internal structure? Transmission electron microscope. That's the example. There's a scanning electron microscope. This is the difference between transmission and light microscope. And these are the preparation, negative staining, shadowing. We briefly mentioned. Okay. This is the one in my research we did an atomic force microscope. If you have question, a certain answer will be there. So it will be stick to the slides basically. It will not be above that. Okay, this is a big one, lecture 3. Okay, what's a big one? Why we can do a staining? Because the bacteria negatively charged and the dye is positively charged. So we can do a basic stain. If the bacteria is negatively charged, the acidic dye also can use is called a negative stain. This is a negative stain. Very important, the gram stain. What are the 4 major steps you should know? Crystal violet, iodine, decoloration alcohol, and counterstain with safranin. Why gram stain stands positive? Why gram stain negative stains, pink, positive stains, crystal violet color, purple? So don't forget cell wall CRE and the lipid CRE. Is that right? We have 2 mentioned in the lecture, and you should go back to see. In my major class, we are required to label these structure. Here, we do not require to do that because it doesn't make any sense. You already know. You can just, you can just know the answer. But in my major class, we're required to do that. Here, you just know the structure is okay. Acid fast stain. Why we use acid fast stain? Because it has a mycolic acids. It's a very waxy cell. Okay, this is used for diagnose tuberculosis, one of the steps. If it's acid fast stain positive, which means it's presumptive positive. Okay, I could ask you a question. If I'm using acid fast stain to diagnose TB, does that mean this guy will 100% have TB? Obviously not, because it's a presumptive positive. The final determination, you have to send it to the reference lab, use transport media. But what we have to do, because tuberculosis, the generation time is very long. It's about like 40 hours, only one generation. The E. coli is relatively short. So that's why the acid fast stain is very important. Okay, that could be a question for you. This we mentioned about indospore stain, capsule stain, and flagella stain. We won't be going too much detail, but I may ask you to list what are the special stain we mentioned, the indospore, capsule, and the flagella. Okay, just maybe a few of the blank questions, simple questions. This is shape and arrangements, and we briefly mentioned, maybe a couple of questions, so true or false, so multiple choice, it's relatively not difficult. And then we go here, we mentioned about, I'm sorry, this slide is gone, I need to put it back. This number 4 slide is gone.